the last topic of we're going to cover on moments is we're going to talk about the principle of moments. So this is used often in 2D cases. So the distributive law, which we talked about for cross product, states that if you have two vectors, in this case we have r cross f, it's equivalent to taking the cross product um, of vector r and the sum of vectors force 1 and force 2, where our force is equal to force 1 plus force 2. Alright, so because of this, what we can say is that our moment, which is equal to r cross f, is equal to the same thing as the cross product of f1 plus f2, which if we distribute that cross product would be the same thing as r cross f1 plus r cross f2. So we can calculate our moment using fx and the fy components of our force. So this would be force 1 and force 2 here, as well as we can also take the same thing, we can do the same thing with our position vector r. Alright, so we can say that we can use rx, we can break r into its components as well to take the cross product here. So if we do that, what we end up getting is we get m naught. Alright, and we're going to do this only in the 2D case, so we're only going to be caring about in 2D the moments due to the forces in the x and the y plane, and the position vectors are also going to be in the xy plane. So the only moments we're going to create are going to be about the z-axis here. So that's why this is a scalar number. We'll write this as r cross f. So if we do that, we could break it down into rxi plus ryj cross fx I plus fyj. If we take the cross product of all these terms, the I cross i's and the j cross j's will equal to 0. So we'll only be left with we'll get this is going to be equal to r of y times f of x plus r of x times f of y. Alright, so this is for the 2D case. Alright, the one thing you have to keep in mind here is you have to look at the signs of your values here. So if we were trying to find the moment about point O here, and we had a position vector r, which would have an x component and a y component. Alright, and then we'd have our force vector f here. It would have an x component, and it would also have a y component. Alright, so just make sure that your these could have like positives or negatives depending on how your forces are or which directions that your forces are acting. So be careful of the signs. Make sure you use the right hand rule to determine whether or not your your moments will be positive or negative. Alright, so the reason we're interested in using the principle of moments is that it's often a lot more convenient to define your position vector and your force vector as Cartesian vectors than it is to find the angle between the two vectors. Alright, so you can find the angle between the two vectors using the dot product between the two vectors, but it sometimes is a lot simpler to just break the forces and the position vectors into components and solve for those forces. And you already did that actually. If we go back to this example here, if you look at force 3 and force 4, and the moment arms for force 3 and force 4, those were actually, that's a perfect example of breaking down the force that's applied at that point and the moment position vector that's applied at that point into their x and their y components, and taking the cross product of those terms individually to determine the total moment about point O. Alright, so that concludes all our lectures on this lecture on moments, calculating a moment about a point in 2 dimensions and also in 3 dimensions using Cartesian vectors.